Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the most mysterious places in the universe, black holes. These strange cosmic objects bend space, slow time, swallow light, and quietly challenge some of our deepest ideas about how reality works. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable, and when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the physics of black holes together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Black holes are often described as monsters of gravity, cosmic traps where nothing, not even light, can escape. But the truth is a little more subtle, and perhaps even more fascinating. Black holes are not just objects drifting through space. They are places where the very structure of the universe becomes stretched, twisted, and folded in unusual ways. To understand them, we have to begin somewhere unexpected. Not with black holes themselves, but with a quiet revolution in how scientists think about gravity. For a long time, gravity seemed simple. If you drop a stone, it falls. If you throw a ball, it arcs through the air. The moon circles the Earth, and the Earth circles the sun. For centuries, scientists described gravity as a force pulling objects toward each other across empty space. It was a powerful idea, and it worked remarkably well. But in the early 20th century, a young physicist named Albert Einstein began to wonder whether gravity might not be a force at all. What if gravity was something stranger? What if space itself could bend? And if space could bend, what might happen to time? As we explore that idea tonight, we'll slowly discover how black holes emerge not from exotic science fiction, but from the quiet mathematics of curved space and flowing time. And it all begins with a simple shift in perspective. Instead of imagining gravity as a pull between objects, imagine the universe as a landscape. Not a landscape of hills and valleys made of rock and soil, but a landscape made of space and time themselves. In this strange landscape, massive objects reshape the terrain. Planets carve gentle valleys, stars create deeper slopes, and when enough mass gathers in one place, the landscape becomes so steep that every possible path leads inward. That is where black holes are born. And so, with that thought gently resting in the background, we begin with the quiet idea that changed our understanding of gravity forever. Imagine placing a smooth sheet of fabric across a wide frame. The fabric is stretched gently in every direction, forming a flat surface. If you roll a small marble across it, the marble glides in a straight line. Nothing unusual happens. But now imagine placing a heavy ball in the center of the sheet. The fabric dips under its weight, forming a shallow valley. Suddenly, when the marble rolls nearby, its path curves. Instead of traveling straight, it begins to bend around the dip in the fabric. For a long time, physicists believed gravity worked in a similar way to an invisible pull between objects. But Einstein suggested something quieter and more elegant. Perhaps objects are not being pulled together at all. Perhaps they are simply following the natural paths created by the shape of space itself. In Einstein's view, space is not empty and rigid. It is flexible. It can stretch, curve, and bend in response to mass and energy. But Einstein went even further. He realized that space and time are not separate things. They are woven together into a single structure often called spacetime, every moment and every location exist within this shared fabric. When a massive object appears, like a planet or a star, it does not simply sit inside space-time, it reshapes it. The presence of mass changes the geometry of the universe around it. Planets follow curved paths around the sun not because they are being pulled like a ball on a string, but because the shape of space-time guides their motion. Physicists sometimes describe these natural paths as the straightest possible routes through curved space-time. In technical language, these paths are called geodesics. But the idea itself is surprisingly simple. Imagine hiking across a gently curved landscape. If you walk straight ahead without turning, your path will naturally follow the slopes and valleys of the terrain. Objects moving through space-time do something similar. They follow the easiest possible path through the curved geometry created by mass. This idea quietly transforms gravity from a force into a feature of geometry. The Earth does not pull the Moon with invisible strings. Instead, the Earth reshapes the nearby space-time, and the Moon moves along the curved paths created by that shape. Even light follows these paths. Although light has no mass, it still travels through space-time, and when space-time bends, the path of light bends with it. This effect is called gravitational lensing. Light passing near a massive object can curve slightly, much like a beam of sunlight bending through a glass lens. Astronomers observe this effect across the universe. Entire galaxies can act as cosmic lenses, bending the light from more distant galaxies behind them. But once you begin thinking of gravity this way, an intriguing question naturally appears. If mass bends space-time, what happens when the mass becomes extremely concentrated? Imagine slowly compressing a star. As the star shrinks, its gravity becomes stronger near the surface. The slopes in the space-time landscape grow steeper. Paths that once curved gently now begin to spiral inward more sharply, keep compressing the star further. Eventually, the slopes become so steep that every possible path in the landscape leads toward the center. Even light, which normally races across the universe faster than anything else, finds that every route it could take bends inward. At that point, the object has crossed a remarkable threshold. The geometry of space-time has changed so dramatically that escape is no longer possible. This is the moment a black hole forms. But it is important to pause here and notice something subtle. Nothing magical happens at that boundary. There is no wall, no sudden explosion of energy, no cosmic trapdoor snapping shut. Instead, the structure of space-time itself quietly shifts. The paths that light and matter can follow begin to curve inward in every possible direction. From the outside, the black hole appears as a dark region where signals can no longer return. Yet from the perspective of the falling traveller, the journey inward might feel surprisingly ordinary at first. The horizon of a black hole is not a physical surface. It is something more abstract and in some ways more fascinating. It is a boundary defined entirely by geometry. And as we continue our slow exploration of black holes, that invisible boundary will become one of the most important ideas in our story. Because once we understand how space-time bends strongly enough to trap light itself, we begin to see how black holes challenge the limits of physics, and perhaps hint at deeper layers of reality waiting quietly beneath the surface of the universe. If gravity is the gentle bending of space-time, then a natural question slowly emerges. What happens when that bending becomes stronger and stronger? Imagine again the stretched fabric we spoke about earlier. When a small marble rolls across a flat sheet, it moves easily in a straight line. When a heavy ball creates a shallow dip, nearby marbles begin to curve around it. But now imagine placing something far heavier in the center of that sheet. The valley deepens, the slopes steepen. Marbles rolling nearby no longer glide past the dip. Their paths spiral inward, circling the heavy object again and again. Now imagine that valley becoming so steep that every possible path slopes downward toward the center. At that point, nothing rolling across the fabric can escape. This simple image, though imperfect, begins to hint at what happens when gravity becomes extremely strong. In Einstein's description of the universe, mass bends spacetime, but when enough mass gathers in a very small region, the curvature of spacetime can become extraordinarily intense. The slopes in the cosmic landscape grow so steep that even light cannot find a path outward. To understand why this happens, physicists often talk about something called escape velocity. Escape velocity is simply the speed an object must reach in order to break free from gravity. On Earth, if you want to launch a rocket into space and never return, the rocket must reach a speed of about 11 kilometers per second. That is roughly 40,000 kilometers per hour. It sounds incredibly fast, but compared to the speed of light, it is still quite modest. The speed of light is about 300,000 kilometers per second. Light moves so quickly that for a long time scientists believed nothing could ever trap it. But gravity grows stronger as mass increases and distance decreases. If an object becomes massive enough, and if that mass is squeezed into a small enough region, the escape velocity near its surface rises dramatically. Imagine compressing the Earth into a smaller and smaller sphere. As the planet shrinks, the gravity near its surface becomes stronger. The escape speed increases. If the Earth were compressed to the size of a marble, its gravity would become so intense that even light would struggle to escape. Of course, Earth will never collapse this way, but massive stars can, and when they do, something remarkable happens. There exists a critical size for any mass. If that mass is compressed inside a certain radius, the escape velocity at the surface becomes equal to the speed of light. This special distance is often called the Schwarzschild radius, named after the physicist Karl Schwarzschild, who discovered the mathematical description of this boundary shortly after Einstein published his theory of general relativity. But for our purposes tonight, we can think of it more simply. It is the distance from the center of an object where gravity becomes so strong that light itself cannot escape. When an object collapses inside this boundary, it forms what we call a black hole. The surface marking that boundary is known as the event horizon. And despite its dramatic name, the event horizon is not a surface you could touch. It has no thickness, no material structure, no glowing wall or cosmic shell. Instead, the event horizon is defined by the geometry of space-time. It marks the place where all possible paths that light could take begin to point inward. To picture this, imagine floating in a river. Far upstream, the current moves gently. You can swim in any direction. Moving against the current requires effort, but it is possible. As you drift closer to a waterfall, the current becomes stronger. Swimming upstream becomes harder. Eventually, you reach a point where the flow of water is so powerful that no swimmer, no matter how strong, could fight against it. Beyond that point, the river inevitably carries everything toward the falls. The event horizon works in a somewhat similar way, except instead of water pulling you along, it is the structure of space-time itself guiding every possible direction inward. Even light, the fastest thing in the universe, cannot turn around once it crosses that boundary. All future paths lead deeper inside. But here is something surprising. From the perspective of someone falling toward a black hole, the event horizon might not feel dramatic at all. If the black hole is large enough, a traveller crossing the horizon would not see a sudden flash or feel a violent shock. The laws of physics behave normally in that local region of space-time. To the falling observer, the journey inward can seem smooth and continuous. Yet to someone watching from far away, the situation appears very different. As an object approaches the event horizon, gravity stretches time itself. clocks closer to the black hole tick more slowly compared with clocks far away. This phenomenon is called gravitational time dilation. It is not science fiction. Experiments on Earth have measured tiny versions of this effect near our planet. Even the satellites used for global navigation system must account for these differences in time. Near a black hole, however, the effect becomes extreme. To a distant observer, a falling object appears to slow down as it approaches the horizon. Its signals become weaker and more stretched. The light it emits shifts toward redder and redder wavelengths. Eventually, the object seems to freeze in place, fading slowly into darkness. Yet the falling traveller experiences something very different. Their own clock continues ticking normally. Their descent continues forward. Both perspectives are valid within Einstein's theory. One observer sees a frozen image at the horizon, the other continues inward. This strange difference in experience is one of the first hints that black holes challenge our everyday understanding of space and time. But the story becomes even more curious, because once an object crosses the event horizon, the geometry of space-time changes in a profound way. The inward direction becomes unavoidable. Just as time carries us from past to future, space-time inside a black hole carries everything toward its center. And somewhere deep inside that hidden region lies one of the most mysterious predictions in all of physics, a place where our equations begin to break down, a place called the singularity. But before we explore that deeper mystery, it helps to understand the boundary that surrounds it. Because the event horizon is not just the edge of a black hole, it is also the doorway into some of the strangest ideas modern physics has ever encountered. When people first hear about black holes, they often imagine a dark cosmic sphere drifting through space like a silent vacuum cleaner, swallowing everything nearby. It is an image that appears often in movies and artwork, a spinning disk of glowing gas, a black circle in the center, a kind of cosmic whirlpool. But the true nature of a black hole is quieter and stranger than that. A black hole is not really an object in the ordinary sense. It is a region of space-time where the geometry of the universe has become so distorted that certain paths simply no longer exist. And the boundary of that region is something physicists call the event horizon. The phrase sounds dramatic, but its meaning is surprisingly simple. The event horizon is the boundary beyond which events can no longer send signals back to the outside universe. Once something crosses that boundary, no information it carries, no light, no message, no signal, can ever reach distant observers again. But perhaps the most surprising part of the story is this. The event horizon is not a surface. It has no thickness, no texture, no physical material. If you were able to drift through the region where the event horizon lies, you would not see a glowing shell or a sudden barrier. Nothing would appear solid or visible in front of you. Instead, the event horizon is defined entirely by the possible paths that light can take through space-time. To understand this idea, physicists often imagine something called a light cone. At every moment in the universe, there are many possible directions a beam of light could travel. Some beams go forward, some backward, some left or right, some upward or downward. If we draw all those possible directions together, they form a shape that resembles a cone. The tip of the cone represents the present moment. The widening shape above it represents all the places light could travel in the future. This light cone is not something you can see in the sky. It is a mathematical picture used to understand how events influence one another across space-time. Normally, these cones are oriented in a balanced way. Light can move outward in many directions. Signals can travel freely from one place to another. But near an extremely massive object, something subtle begins to happen. The curvature of space-time gradually tilts the light cones inward. At first, the effect is small. Light travelling near a massive, Star bends slightly. Astronomers have observed this bending many times when starlight passes near the Sun. Closer to a dense object like a neutron star, the bending becomes stronger, and near a black hole, the tilting becomes dramatic. The cones that describe all possible future directions begin to lean inward toward the center. Imagine standing on a hillside that becomes steeper and steeper the farther you go. Walking straight ahead gradually turns into walking downhill. Eventually, every path leads downward. The light cones near a black hole behave in a similar way. At the event horizon, the cones tilt so far inward that the outward direction disappears completely. Light can still move forward in time, but every possible forward path now points toward the center of the black hole. From that moment onward, the future of anything crossing the horizon lies deeper inside. Nothing can turn around. Not because there is a force holding it in place, but because space-time itself has changed, the shape of possible motion. Even light, which always travels at the fastest speed allowed by nature, cannot find a route outward. All paths lead inward. This is why the event horizon marks the true boundary of a black hole. It is not the edge of a physical object. It is the place where the geometry of space-time removes the possibility of escape. Yet despite this dramatic description, crossing the event horizon might not feel extraordinary at all. If the black hole is large enough, the gravitational forces at the horizon can be quite gentle. A traveller drifting across that boundary might notice nothing unusual in that moment. No sudden flash, no sharp impact, just a quiet continuation of the journey inward. Meanwhile, far away in the universe, distant observers would see something very different. As the traveller approaches the horizon, the signals they send outward take longer and longer to escape. The light waves stretch as they climb out of the intense gravity. Their colour shifts, gradually toward deeper and deeper shades of red. This effect is known as gravitational redshift. You can imagine it like the sound of a train whistle fading as the train moves farther away, except here the stretching happens because light is climbing out of curved space-time. Eventually the signals become so stretched that they fade beyond detection. To distant observers, the traveller appears to slow down near the horizon. Their movements grow slower and slower. The light they emit becomes dimmer and redder. In a sense, they appear frozen at the edge. But this frozen image is an illusion created by the stretching of time. For the traveller themselves, time continues normally. Their own clock ticks at its usual rhythm. They pass the horizon and continue inward. This strange difference between viewpoints is one of the most beautiful aspects of Einstein's theory. Different observers can describe the same event in different ways, and yet the underlying laws of physics remain consistent. But the deeper one looks at black holes, the more unusual the story becomes, because once an object passes beyond the horizon, the geometry of space-time changes even more dramatically. Outside a black hole, you can choose whether to move closer to a massive object or farther away. Inside a black hole, that choice disappears. Moving toward the center becomes as unavoidable as moving forward in time. No rocket engine, no beam of light, no clever maneuver can change that direction. Every possible future path leads deeper inside, and somewhere in that hidden interior lies a prediction that has puzzled physicists for decades. A point where the curvature of space-time grows without limit. A place where our equations, as powerful as they are, begin to lose their meaning. It is called the singularity, and it may represent not just the center of a black hole, but the edge of our current understanding of the universe. If black holes reveal anything truly strange about the universe, it may not be their darkness or their gravity, but their relationship with time. We usually imagine time as something steady and reliable. Seconds pass at the same rhythm everywhere. Clocks tick forward in quiet agreement. A minute in one place is the same as a minute in another. But Einstein's theory quietly tells a different story. Time does not flow at exactly the same rate everywhere in the universe. Instead, the flow of time depends on the structure of space-time itself. Where gravity is weak, time moves almost exactly as we expect. But where gravity becomes strong, time begins to slow. This effect is called gravitational time dilation. The phrase may sound technical, but the idea itself can be understood with a simple picture. Imagine two identical clocks. One clock remains far from any strong gravitational field, floating peacefully in deep space. The second clock is lowered toward a massive object, like a neutron star or a black hole. If we could watch both clocks, from a safe distance, we would notice something subtle but measurable. The clock closer to the massive object ticks more slowly than the one far away. Each second near the strong gravity stretches slightly longer compared with the seconds experienced far away. This is not a flaw in the clocks. The clocks themselves are working perfectly. Instead, the difference arises because gravity changes the rhythm of space-time itself. Time flows differently depending on where you are. On Earth, this effect is tiny, but real. Clocks placed on mountains tick slightly faster than clocks at sea level. The difference is small, measured in billionths of a second, but modern instruments can detect it. Even the satellites that help our navigation systems function must account for this effect. Their onboard clocks experience slightly different gravitational conditions than clocks on the ground, and without correction, the system would slowly drift out of accuracy. Near a black hole, however, the stretching of time becomes extraordinary. As you move closer to the event horizon, the gravitational field grows stronger. The curvature of space-time deepens, and the flow of time, relative to distant observers, slows dramatically. Imagine again the traveller approaching a black hole. From the traveller's perspective, their own watch continues ticking normally. Their heartbeat feels steady. Their thoughts unfold at their usual pace. But far away, someone watching through a powerful telescope would see something different. As the traveller moves closer to the event horizon, their clock appears to slow down. At first, the difference is subtle. Seconds become slightly longer. Movements grow a little slower. But as the traveller approaches the horizon itself, the slowing becomes extreme. From the distant observer's viewpoint, the traveller seems to move in slow motion. Every gesture stretches across longer and longer intervals of time. Eventually, the traveller appears almost frozen at the edge. Their signals grow dim. The light they emit becomes stretched into longer wavelengths, shifting toward deeper shades of red. This is the same phenomenon we mentioned earlier, known as gravitational redshift. It happens because light climbing away from strong gravity loses energy as it escapes the curved space-time around the black hole. But here is the strange part. For the traveller themselves, nothing unusual happens at that exact moment. They cross the event horizon in finite time according to their own clock. Their watch ticks normally. Their journey continues inward. This difference between perspectives can feel confusing at first, but it reflects a deeper truth about relativity. Time is not absolute. Different observers moving through different regions of space-time can experience time differently, and both experiences can be equally valid within the laws of physics. To visualize this, imagine two hikers walking through a valley at different elevations. One walks along the valley floor, the other travels high along the ridge above. Each hiker follows a different path across the landscape. The distance they travel and the time it takes may differ depending on the route they choose. In a similar way, objects travelling through space-time follow paths shaped by gravity. Those paths determine how time unfolds along the journey. Near a black hole, the paths through space-time become dramatically curved. The deeper the curvature, the more stretched time appears from far away. But even this strange effect is only the beginning. because the closer we move toward the center of a black hole, the more unusual the geometry of space-time becomes. Near the horizon, the structure of space-time already forces light cones to tilt inward, guiding every possible future path toward the center. Deeper inside, the geometry changes even more radically. Outside the horizon, you can move toward or away from the center of gravity. Inside the horizon, moving toward the center becomes unavoidable. It becomes part of the future itself. Just as none of us can choose to stop time from moving forward, nothing inside the horizon can avoid moving toward the interior of the black hole. In that sense, falling toward the center of a black hole is not like falling toward a planet. It is more like moving toward tomorrow. The direction becomes part of the structure of space-time, and somewhere ahead along that inevitable path lies the most mysterious prediction of Einstein's equations. A place where space-time curvature grows so extreme that the mathematics describing it begins to fail. A place where density and curvature appear to become infinite. Physicists call this place the singularity. Whether the singularity truly exists in nature remains one of the great open questions in modern science. Because when our equations produce infinities, it usually means something deeper is waiting to be discovered, and black holes may be pointing us toward a new understanding of the universe. One that connects gravity, quantum physics, and information in ways we're only beginning to explore. But before we look deeper into that mystery, we first need to understand what happens to space and time themselves once the horizon has been crossed. Because inside a black hole, the structure of space-time behaves in ways that challenge even our most careful intuition. As we have seen, gravity does more than pull objects together. It quietly reshapes space-time, bending both space and time in ways that can stretch or compress the rhythm of the universe. Near a black hole, this stretching becomes dramatic. From far away, the clock of a falling traveller appears to slow, almost to a stop as it approaches the event horizon. Yet from the traveller's own perspective, their watch continues ticking normally. At first, this seems impossible. How can time move normally for one observer and slowly for another? The answer lies in one of the most profound ideas in Einstein's theory of relativity. Time is not a universal river flowing at the same speed everywhere. Instead, time depends on the path you take through space-time. To explore this idea, imagine two identical clocks again. One clock remains far from the black hole, drifting peacefully in deep space. The other begins a slow descent toward the gravitational well of the black hole. Both clocks are perfectly accurate. Both measure time faithfully according to their own surroundings, but they are travelling along different paths through space-time. The clock far away moves along a relatively gentle region of space-time, where curvature is small and time flows in the familiar rhythm we experience every day. The clock falling toward the black hole moves through a much more curved region of space-time, where gravity stretches the geometry of the universe itself. Because of this difference in curvature, the two clocks do not accumulate time in exactly the same way. Each clock measures what physicists sometimes call its own personal time, the time experienced along its particular journey through space-time. In technical language, this is known as proper time. But the idea is simple. Proper time is the time measured by a clock travelling with you, ticking along the path you follow through the universe. Meanwhile, a distant observer describes events using a different kind of time, sometimes called coordinate time. This is the time measured by clocks that remain far away from the intense gravitational field. Neither description is wrong. They simply describe the same physical situation from different vantage points. To make this easier to picture, imagine two travellers hiking across a wide landscape. One traveller walks across a flat plain, taking a direct route between two distant hills. The other traveller chooses a winding trail through a deep valley. both travellers eventually arrive at the same destination. But the distances they walked and the time required for their journeys may differ because the terrain shaped their paths. Space-time behaves in a similar way. The presence of gravity curves the landscape through which objects move. Two observers travelling along different routes through that landscape can experience different amounts of time. Near Earth, these differences are small. Near a black hole, they become astonishing. A clock hovering just above the event horizon may tick extremely slowly compared with a clock far away in space. From the distant perspective, hours near the black hole could correspond to years passing in the wider universe. This idea sometimes appears in science fiction stories, where astronauts travelling near strong gravity return home to find that many years have passed while only a short time passed for them. Although those stories are dramatic, the underlying physics is real. Gravitational time dilation has been measured with high precision in laboratories and in orbiting satellites. Black holes simply magnify the effect to extraordinary levels. But the strange differences between observers go even deeper than the ticking of clocks. Because in Einstein's universe, not only time but also the very structure of cause and effect is shaped by space-time geometry. This brings us back to the image of the light cone we discussed earlier. The light cone represents all the directions that light, and therefore any signal, can travel from a given event. Outside a black hole, the cone spreads outward in many directions. Signals can travel to distant regions of the universe. But as one approaches the event horizon, the curvature of space-time tilts the cone inward. The possible directions that light can travel begin to lean toward the centre of the black hole. At the horizon itself, something remarkable happens. The outward direction becomes exactly balanced at the edge. Light trying to move outward simply remains at the boundary. Beyond that boundary, the tilt becomes so strong that every possible future direction points inward. This is why escape becomes impossible. Not because gravity pulls infinitely hard, but because the geometry of space-time removes every outward path. And this geometric view helps explain why different observers can disagree about the timing of events near a black hole. From the distant observer's perspective, the traveller never quite crosses the horizon. Their signals become stretched and delayed, making the crossing appear to take longer and longer. From the traveller's perspective, the crossing happens naturally and quickly. Both descriptions arise from the different ways each observer measures time and distance through space-time. It is a bit like watching a boat drift toward a distant fog bank. From far away, the boat appears to slow as it approaches the mist, gradually fading from view. But to the passengers aboard the boat, the journey continues smoothly forward. Black holes create a similar illusion, except that the fog bank is not made of water droplets. It is made of the structure of space-time itself, and once the traveller moves beyond that invisible boundary, the geometry of space-time becomes even stranger. Outside the horizon, you can choose whether to move closer to a massive object or farther away. Inside the horizon, that freedom disappears. Moving inward becomes part of the future itself. Just as none of us can choose to stop time from advancing toward tomorrow, nothing inside the horizon can avoid moving deeper toward the centre. This extraordinary property hints that space and time may exchange roles inside a black hole. Directions that once behaved like ordinary space begin to act more like time, and directions that once behaved like time begin to resemble spatial dimensions. The deeper one looks into these strange geometries, the clearer it becomes that black holes are not merely astronomical objects. They are laboratories where the fabric of reality reveals its most unusual patterns, and to understand what truly lies inside them we must now follow the traveller beyond the horizon into the hidden region where space-time itself begins to change character. Up to this point in our journey, we have been standing outside the black hole. watching the strange behaviour of time and light from a safe distance. We've seen how clocks appear to slow near the event horizon, and how the geometry of space-time bends so strongly that light itself cannot escape. But now let us imagine something a little more daring. Imagine drifting slowly past the event horizon and continuing inward. What happens next is one of the most surprising predictions of Einstein's theory. Because inside a black hole, the familiar roles of space and time begin to change. To understand this idea, it helps to think again about the way we move through everyday life. In ordinary space, you have freedom of direction. You can walk north or south, left or right, forward or backward. Space allows choice. You decide where to go. Time behaves differently. No matter how hard you try, you cannot decide to move backward through yesterday or pause the arrival of tomorrow. Time carries us forward in a single direction. In physics language, time has an arrow. It moves from past to future, and we cannot turn around within it. Outside a black hole, space and time behave in the familiar way we expect. We move freely through space, while time quietly carries us forward. But the geometry of space-time near a black hole becomes so strongly curved that these roles begin to shift. The key to this transformation lies again in the idea of the light cone. Earlier we described the light cone as a picture of all the possible directions that light, and therefore any signal, can travel from a particular event. Outside the black hole, the light cone spreads outward, allowing signals to travel in many directions across space, while always moving forward in time. But as one approaches the event horizon, the curvature of space-time tilts the cone inward. Near the horizon, the outward direction becomes harder and harder to reach. At the horizon itself, the light cone tips so far that the outward direction lies exactly along the boundary. Light trying to move outward simply remains suspended at the edge. Once inside the horizon, something remarkable occurs. The cone tilts completely inward. Every possible future direction now points toward the centre of the black hole. This means that moving toward the centre is no longer just one option among many. It becomes the inevitable direction of the future itself. In other words, falling toward the centre of the black hole becomes as unavoidable as moving forward in time. This is the moment when space and time begin to exchange roles. Outside the black hole, distance from the centre behaves like ordinary space. You can move inward or outward if you choose. Inside the black hole, moving inward behaves more like time. It is something that happens inevitably as the future unfolds. Trying to avoid the centre would be like trying to avoid tomorrow. No engine, no beam of light, no clever manoeuvre could change that direction. To picture this idea, imagine standing at the top of a steep mountain valley during a powerful storm. Rainwater rushes downhill in fast-moving streams. Small branches and leaves float along with the current. At the upper slopes, the water moves gently. A leaf might drift in different directions depending on the wind. But deeper in the valley, the flow becomes stronger and more focused. Eventually, the current becomes so powerful that every floating object is carried downstream. Inside a black hole, space-time behaves in a somewhat similar way. The geometry itself guides all future motion inward. Even light, which always travels at the fastest possible speed, cannot find a path that leads outward once the horizon has been crossed. But this does not mean that everything instantly crashes into the centre. The journey inward still takes time according to the falling traveller's clock. For a black hole formed from a massive star, the traveller might have a few moments before reaching the central region. For a supermassive black hole, like the ones believed to exist at the centres of galaxies, the journey could last much longer. During this descent, the traveller would experience increasingly intense gravitational effects. Gravity near the centre changes rapidly with distance. The difference in gravitational pull between your feet and your head grows larger and larger. This stretching effect is sometimes called tidal gravity. If the difference becomes strong enough, objects can be stretched into long, thin shapes as they fall inward. Scientists sometimes refer to this process with a slightly playful name, spaghettification. The name may sound humorous, but it reflects a serious physical effect. Strong tidal forces can stretch and compress objects dramatically. However, the strength of this effect depends on the size of the black hole. For smaller black holes, the tidal forces near the horizon are extremely strong. But for supermassive black holes, those millions or billions of times heavier than the Sun, the horizon itself may be relatively gentle. A traveller might cross it without noticing dramatic stretching at that moment. Only deeper inside would the tidal forces become overwhelming. But regardless of the details of the journey, one destination lies ahead along every possible future path: the centre of the black hole. In Einstein's equations, this central region appears as a point where the curvature of spacetime becomes infinitely large. Density grows without bound. The mathematical description of spacetime itself breaks down. Physicists call this region the singularity. It is important to understand what that word really means. A singularity does not necessarily represent a physical point that truly exists in nature. Instead, it often signals that the theory we are using has reached its limits. It is like following a map until the road suddenly disappears into blank space. The map has brought us as far as it can go, but the territory continues beyond it. General relativity, the theory Einstein developed to describe gravity, works beautifully across an enormous range of situations. It explains the motion of planets, the bending of light by stars, and the expansion of the universe itself. But near the singularity of a black hole, the theory predicts infinities, and infinities in physics usually indicate that a deeper theory is waiting to be discovered. Many physicists believe that understanding what truly happens at the centre of a black hole will require combining Einstein's theory of gravity with the strange rules of quantum physics. That union, sometimes called quantum gravity, remains one of the greatest challenges in modern science, and black holes may be the places where that deeper understanding finally reveals itself. As we follow our imagined traveller deeper into the hidden interior of a black hole, the geometry of space-time continues to grow more extreme. The curvature becomes stronger, the inward pull becomes unavoidable, and every possible future path continues to guide matter and light toward the centre. According to Einstein's equations, this journey eventually leads to a region where the curvature of space-time becomes infinitely large. Physicists call this region the singularity. The word itself sounds mysterious, but its meaning is surprisingly practical. In physics, a singularity is not necessarily a physical object. Instead, it is a signal that our mathematical description of nature has reached its limits. It is the point where the equations stop making sense. To understand why this happens, imagine drawing a map of a mountain range. The map might show roads, valleys, rivers, and slopes with great accuracy. But if the terrain suddenly drops into a vertical cliff or disappears into a deep cavern, the map might not capture those features correctly. At that point, the map is not wrong. It has simply reached the edge of its usefulness. In a similar way, Einstein's theory of general relativity gives us an extraordinarily powerful map of gravity. It describes how mass and energy curve space-time and how objects move along those curved paths. For more than a century, the theory has passed every experimental test scientists have been able to perform. It predicts the motion of planets with remarkable precision. It explains the bending of starlight near massive objects. It even predicted the existence of gravitational waves, ripples in space-time that were finally detected by sensitive instruments on Earth in the year 2015. Yet inside a black hole, the equations of general relativity lead us toward a mathematical cliff. As the collapsing matter approaches the centre, the density grows larger and larger. The curvature of spacetime becomes more and more intense. In the equations, these quantities grow without bound, they approach infinity. But in physics, infinities are usually a warning sign. They suggest that the theory we're using is incomplete. To see why this might be the case, we must remember that general relativity describes gravity on very large scales. It works beautifully for planets, stars, galaxies, and the expansion of the universe. But the microscopic world, the world of atoms and particles, is governed by a different set of rules known as quantum physics. Quantum physics describes nature in terms of probabilities, fluctuations, and tiny packets of energy. Most of the time, these two theories coexist peacefully because they describe different domains of nature. General relativity governs the large-scale structure of space-time. Quantum physics governs the tiny building blocks of matter and radiation. But inside a black hole, these two realms collide. The region near the singularity combines enormous gravitational forces with incredibly small distances. Under those conditions, both gravity and quantum effects should become important at the same time, and yet our current theories cannot fully describe that situation together. General relativity predicts the singularity, where curvature becomes infinite. Quantum physics suggests that nature rarely allows such infinities to exist. Somewhere in that conflict lies a deeper truth that scientists are still trying to uncover. Many researchers believe that the singularity predicted by Einstein's equations may not exist in reality as an infinitely dense point. Instead, the true structure of space-time near the centre of a black hole may be governed by a new theory that merges gravity with quantum physics. This future theory is often called quantum gravity. Quantum gravity remains one of the greatest unsolved problems in modern science. Physicists have proposed many ideas about how such a theory might work. Some approaches suggest that space-time itself may be made of tiny discrete units like grains in a vast cosmic fabric. Others propose that space-time may emerge from deeper layers of information encoded in quantum systems. Still others explore the possibility that the interior of a black hole connects to other regions of space-time in unexpected ways. At the moment, these ideas remain active areas of research rather than established facts, but black holes provide the perfect natural laboratories for exploring these questions, because nowhere else in the universe do we find such extreme combinations of gravity, density, and energy. And even though the singularity itself remains hidden behind the event horizon, its existence shapes many of the mysteries surrounding black holes. For example, if information about matter falling into a black hole ultimately reaches the singularity and disappears, then something profound would happen. One of the core principles of quantum physics says that information about the state of a system cannot be destroyed. It can change form, it can become scrambled or difficult to recover, but it should never vanish completely. Black holes challenge this principle. Matter-carrying information can fall inside the horizon, but if the singularity truly destroys that information, then quantum physics itself might need revision. This puzzle is known as the information paradox. It is one of the most important unsolved questions in theoretical physics. For decades, scientists have debated whether information is truly lost inside black holes or whether some subtle process allows it to survive. The answer may reveal something fundamental about the nature of space-time itself, but before we explore that puzzle more deeply, we must first understand the different forms that black holes can take. Because not all black holes are identical. Some rotate, some may carry electric charge, some exist as the remnants of dying stars, while others grow to enormous sizes at the centres of galaxies. Each of these variations reveals a different aspect of how gravity shapes the universe. And by studying them, scientists have learned that black holes are not just theoretical curiosities, they are real, powerful engines that influence the evolution of stars galaxies, and perhaps even the structure of the cosmos itself. So far, our journey has taken us through the strange geometry surrounding black holes and the mysterious interior predicted by Einstein's theory. We have seen how space-time bends so deeply that light cannot escape, and how the equations of gravity eventually lead us to a region where they can no longer fully describe what happens. But long before physicists began debating the mysteries of singularities and quantum gravity, they first asked a simpler question. If a black hole exists, what does it look like from the outside? Not in the sense of colour or brightness, but in terms of the mathematical structure of space-time around it. To answer this question, scientists turn to Einstein's equations of general relativity. These equations describe how mass and energy shape the geometry of space-time. Soon after Einstein introduced the theory in the early 20th century, a German physicist named Karl Schwarzschild found the first exact mathematical solution describing the gravitational field around a perfectly simple object. In Schwarzschild's solution, the object has only one property: mass. It does not spin. It carries no electric charge. It is perfectly spherical, like a smooth ball of gravity. Although this situation is idealized, it provides a powerful starting point for understanding black holes. The space-time around such an object has a clear and elegant structure. At a certain distance from the center lies the event horizon, the boundary where escape becomes impossible. Outside that boundary, space-time curves gently. Objects can orbit the black hole just as planets orbit a star. Inside that boundary, every future path leads inward. The size of this horizon depends entirely on the mass of the black hole. A more massive black hole has a larger horizon. A smaller black hole has a smaller one. For example, if our Sun were somehow compressed into a black hole without changing its mass, the event horizon would have a radius of only about 3 kilometers. That means the entire Sun would need to be squeezed into a sphere roughly the size of a small city. The Earth, if compressed into a black hole, would have an event horizon less than the size of a coin. Of course, neither the Sun nor the Earth is capable of collapsing this way under normal conditions. But these examples help illustrate how incredibly dense black holes must be. And yet, despite their density, the outside behaviour of a simple black hole turns out to be surprisingly minimal. In fact, physicists discovered a remarkable principle known as the no-hair theorem. The name is playful, but the idea behind it is profound. The theorem states that once a black hole forms, nearly all the detailed information about the matter that created it disappears from the outside universe. From the perspective of distant observers, a black hole can be described using only 3 basic properties: its mass, its rotation, and its electric charge. Everything else, the chemical composition of the original star, the shape of the collapsing matter, the details of the material that fell in, becomes hidden behind the horizon. In a sense, the black hole forgets its past. No matter what formed it, the external gravitational field eventually settles into a very simple form, determined only by those few properties. This remarkable simplicity is one of the reasons black holes are such powerful objects for theoretical physics. Despite being born from complicated astrophysical events, their final structure becomes elegantly simple. For the Schwarzschild black hole, the simplest type, only one property matters: mass. Because it does not rotate, the space-time around it remains perfectly symmetrical in every direction. If you could hover near such a black hole, you would find that gravity behaves exactly the same no matter which direction you face. But even in this simple case, the geometry of space-time reveals fascinating features. For instance, there exists a special region outside the event horizon where light can orbit the black hole. At this distance, the curvature of space-time bends light into a circular path. Photons, particles of light, can travel around the black hole like runners circling a track. This region is sometimes called the photon sphere. However, these orbits are unstable. A slight disturbance would cause the light to spiral inward toward the horizon or escape outward into space. This delicate balance of light circling a black hole plays an important role in the images astronomers have captured of real black holes. When telescopes combine signals from observatories spread across the Earth, they can detect the shadow created by this region of orbiting light. The dark center seen in these images is not the black hole itself, but the silhouette formed by the pairs of light near the photon sphere. Surrounding that shadow is a glowing ring created by gas heated to extraordinary temperatures as it spirals toward the horizon. These observations provide some of the most direct evidence we have that black holes truly exist. Yet the Schwarzschild black hole represents only the simplest possibility allowed by Einstein's equations. In reality, most black holes are unlikely to remain perfectly still. Stars rotate, galaxies rotate, and the collapsing material that forms a black hole almost always carries angular momentum, the physical quantity associated with rotation. As a result, many black holes spin, and when a black hole spins, the surrounding space-time begins to behave in even more unusual ways. Rotation twists the geometry of space-time itself, dragging nearby space along with it, like water swirling around a spinning drain. In the next part of our journey, we will explore these rotating black holes and the extraordinary regions they create. Because once a black hole begins to spin, the universe around it becomes even more dynamic and even more mysterious. The black hole we explored in the previous session was the simplest possible version. A quiet, perfectly symmetrical object defined only by its mass. In that ideal picture, the black hole does not rotate. Space-time curves smoothly around it like a deep, round valley. But in the real universe, things are rarely so still. Stars spin, clouds of gas spin, entire galaxies rotate slowly across cosmic time. When a massive star collapses to form a black hole, it almost always carries some of that rotation with it. And when a black hole spins, something remarkable happens. The rotation does not affect only the matter falling into the black hole, it also affects space-time itself. To understand this, imagine stirring a spoon slowly through a bowl of honey. As the spoon turns, the thick liquid around it begins to swirl. Nearby droplets are dragged along by the motion. The spinning object pulls the surrounding fluid into its rotation. A spinning black hole behaves in a similar way. But instead of dragging honey or water, it drags space-time. Physicists call this effect frame dragging. The phrase may sound technical, but the idea is surprisingly visual. Space itself begins to twist around the rotating black hole. The faster the black hole spins, the stronger this twisting becomes. If you could hover near such a black hole and watch the motion of nearby particles, you would notice that nothing remains completely still. Even objects trying to remain stationary are gently pulled into motion by the spinning geometry of space-time. It is as if the universe around the black hole has been caught in a slow cosmic whirlpool. The mathematical description of a rotating black hole was discovered by a physicist named Roy Kerr in the 1960s. His solution to Einstein's equations revealed that rotating black holes have a richer structure than the simple Schwarzschild case we discussed earlier. One of the most intriguing features created by rotation is a region known as the ergosphere. The ergosphere surrounds the black hole just outside the event horizon. It is shaped somewhat like a flattened bubble wrapped around the spinning object. Inside this region, space-time is dragged so strongly that remaining motionless becomes impossible. Even light cannot remain stationary there. Everything must move in the direction of the black hole's rotation. But unlike the event horizon, the ergosphere is not a point of no return. Objects entering this region can still escape, provided they move quickly enough in the right direction. This strange property leads to one of the most fascinating possibilities in black hole physics. Under certain conditions, energy can actually be extracted from the rotation of a black hole. At first, this sounds impossible. Black holes are often described as cosmic traps, swallowing everything that approaches them. Yet the spinning geometry of spacetime opens a subtle loophole. Imagine a particle entering the ergosphere and splitting into two pieces. One piece falls deeper toward the black hole. The other escapes outward. If the split happens in just the right way, the escaping piece can leave with more energy than the original particle had when it entered. Where did that extra energy come from? It comes from the rotation of the black hole itself. The process effectively slows the spin of the black hole by a tiny amount, transferring some of its rotational energy to the escaping particle. Physicists call this phenomenon the Penrose process, named after the mathematician Roger Penrose, who first described the idea. While this process is extremely difficult to achieve in practice, it demonstrates an important principle. A rotating black hole is not merely a passive gravitational object. It stores enormous amounts of rotational energy within the twisting structure of spacetime around it. In fact, astrophysicists believe that similar mechanisms may power some of the most energetic phenomena in the universe. Near certain black holes, especially the supermassive ones found at the centers of galaxies, enormous jets of energy shoot outward into space. These jets can extend for thousands of light years, carrying streams of particles moving close to the speed of light. Although the full mechanism behind these jets is complex and still under investigation, many scientists believe that the rotation of black holes and the magnetic field surrounding them play a key role in launching these cosmic beams. In this way, black holes, once thought to be purely destructive objects, may actually act as powerful engines shaping their cosmic environments. Rotation also changes the structure of the black hole's interior. In the simplest non-rotating case, the singularity appears as a point hidden at the center. In the rotating case described by the Kerr solution, the singularity takes on a different mathematical form. Instead of a point, it becomes something more like a ring. This ring-shaped structure appears in the equations describing the rotating black hole, though what it represents physically remains uncertain. Because the region near the singularity lies beyond the limits of our current theories, physicists treat these predictions cautiously. The mathematics suggests intriguing possibilities, including connections to other regions of spacetime. But without a complete theory of quantum gravity, it is difficult to know which of these predictions reflect reality and which are artifacts of incomplete equations. Still, the discovery of rotating black holes revealed an important truth. Black holes are not simple cosmic voids. They are dynamic objects with structure, motion, and energy. Their rotation twists space-time, alters the paths of particles and light, and may even power some of the brightest phenomena in the universe. And yet, as strange as rotating black holes may seem, they are only one part of a much larger story. Because the black holes we observe across the universe are not isolated mathematical curiosities. They are born from the dramatic deaths of stars. They grow by feeding on gas and dust. They merge with one another in powerful cosmic collisions. To understand where these extraordinary objects come from, we must now step away from the mathematics of space-time and turn our attention to the life cycles of stars themselves. When we imagine a black hole, we often picture a place where everything disappears forever. Matter falls inward, light cannot escape, and the black hole quietly grows heavier as it consumes whatever drifts too close. But the story becomes more interesting when a black hole is spinning. Rotation changes the structure of space-time around the black hole in subtle but powerful ways. In the previous session, we explored the region called the ergosphere, where the twisting of space-time becomes so strong that nothing can remain perfectly still. Inside that region, everything must move along with the rotation. This strange behaviour opens the door to one of the most surprising ideas in theoretical physics. Under the right conditions, it is possible to extract energy from a spinning black hole. At first, this seems impossible. After all, the black hole is the most powerful gravitational trap in the universe. How could anything escape with extra energy? The answer lies in the peculiar geometry of the ergosphere. Imagine a spacecraft drifting carefully toward a rotating black hole. As it enters the ergosphere, the twisting motion of space-time begins to carry the craft along in the direction of the black hole's spin. The spacecraft can still escape if it fires its engines in the right direction, but the region behaves a little like a powerful current in a river. Within that current, an unusual maneuver becomes possible. Suppose the spacecraft releases two small probes connected by a cable. At the right moment, the cable snaps and the probes separate. One probe falls inward toward the black hole, while the other escapes outward. If the split happens in exactly the right way, something remarkable occurs. The escaping probe can leave the ergosphere with more energy than the original spacecraft had when it entered. In other words, the escaping object gains energy. The extra energy does not appear from nowhere. It comes from the rotation of the black hole itself. The black hole loses a tiny portion of its spin, and that rotational energy is transferred to the escaping object. This theoretical mechanism was first described by the physicist Roger Penrose, and it is known as the Penrose process. Although the original idea involved splitting particles, scientists now believe that nature may perform similar tricks on a much larger scale. Around many black holes, swirling disks of gas and dust form as matter spirals inward. These structures are known as accretion disks. The gas in these disks becomes incredibly hot as it falls toward the black hole, glowing brightly across the electromagnetic spectrum. Powerful magnetic fields form within the disk as charged particles move through the rotating environment. When these magnetic fields interact with the spinning spacetime near the black hole, they can channel energy outward in narrow beams called relativistic jets. These jets shoot out along the rotation axis of the black hole, often extending thousands or even millions of light years into space. Within these jets, particles travel at speeds very close to the speed of light. Seen from Earth, these jets appear as brilliant streams of energy emerging from the centers of distant galaxies. Although the exact details are still being studied, many astrophysicists believe that the rotational energy of black holes plays a crucial role in powering these enormous structures. In this way, black holes may act less like cosmic vacuum cleaners and more like powerful engines. They swallow matter, but they also release tremendous amounts of energy back into the surrounding universe. Another fascinating consequence of black hole rotation involves the paths that light can take near the horizon. In the simplest, non-rotating case, light can orbit the black hole along a narrow spherical region known as the photon sphere. But when the black hole spins, the situation becomes more complicated. The twisting of space-time causes light travelling in the direction of the black hole's rotation to behave differently from light travelling against the rotation. One direction becomes slightly easier for light to follow, while the opposite direction becomes more difficult. As a result, the glowing rings of light surrounding real black holes can appear distorted and asymmetric when observed with powerful telescopes. These distortions help astronomers measure the spin of black holes by studying how light behaves near the horizon. The faster the black hole rotates, the more strongly space-time is dragged along with it. Over time, the black hole can lose some of this rotational energy through interactions with surrounding matter and magnetic fields. But even with these losses, many black holes retain enormous amounts of spin. Some are believed to rotate hundreds of times per second, carrying vast reservoirs of energy within the twisting structure of space-time. The idea that a black hole can store and release energy might seem surprising, but it fits naturally within Einstein's description of gravity. In general relativity, energy is not just contained within matter. It can also be stored in motion, curvature, and fields. A rotating black hole is a dramatic example of this principle. Its spin is not merely a property of the object itself, it reshapes the surrounding geometry of space-time, creating regions where energy can be exchanged in ways that have no ordinary counterpart in everyday physics. Yet even this complex picture is still only part of the story. So far we've discussed black holes that possess mass and rotation, the two most important properties found in nature. But the equations of general relativity allow for even more exotic possibilities. In theory, black holes could also carry electric charge, and the mathematical solutions describing them reveal additional layers of complexity. Although such charged black holes are unlikely to exist in large numbers in the universe, studying them helps physicists explore the full range of structures that space-time can take under extreme conditions. And these explorations sometimes lead to ideas that stretch the imagination even further. Ideas involving tunnels through space-time, unusual internal geometries, and the possibility that black holes may connect distant regions of the cosmos in ways we do not yet fully understand. Before venturing into those more speculative possibilities, however, it helps to return briefly to the origins of black holes themselves. Because black holes are not simply mathematical solutions in Einstein's equations, they're real astrophysical objects born from some of the most dramatic events in the life cycle of stars. As physicists explored the equations describing black holes, they gradually discovered something both exciting and slightly unsettling. Einstein's equations do not describe just one kind of black hole. They describe many possible structures, some simple, some rotating, and some far stranger than anything we have ever observed. Up to now, we have mostly focused on black holes defined by two main properties: mass and rotation. These are the types astronomers believe actually exist in the universe. But the mathematics of general relativity allows additional possibilities. For example, a black hole could also carry electric charge. In everyday life, electric charge is familiar. It is the property responsible for electricity and magnetism. Charge particles attract or repel one another depending on their sign. If a collapsing star somehow retained a large electric charge, the resulting black hole would not only curve space-time through gravity, it would also create strong electric fields surrounding it. The equations describing such objects predict black holes, with structures slightly different from the ones we've discussed so far. In practice, however, large electric charges are unlikely to persist in real astrophysical black holes. The universe contains many charged particles, and any large imbalance would quickly attract opposite charges that neutralize the system. For this reason, most black holes we expect to observe are nearly electrically neutral. Still, exploring these mathematical possibilities helps physicists understand the full range of solutions allowed by Einstein's theory, and some of those solutions lead to ideas that feel almost like science fiction. Earlier we mentioned that the interior of a rotating black hole may contain a ring-shaped singularity rather than a single point. In the mathematical description, this ring creates unusual pathways through space-time. In certain idealized solutions, the equation suggests that space-time might extend beyond this ring into other regions. Some researchers have wondered whether these structures could resemble tunnels connecting distant parts of the universe. These hypothetical tunnels are often called wormholes. The name comes from a simple image. Imagine a worm crawling through an apple. Instead of travelling across the surface, the worm tunnels through the interior, connecting two distant points with a much shorter path. A wormhole in space-time would behave in a somewhat similar way. Instead of travelling across the vast distances between stars or galaxies, a traveller might theoretically pass through a shortcut connecting two far separated regions. The mathematics, describing certain black hole solutions, sometimes contain structures that resemble these tunnels. But there is an important caution here. Mathematical possibilities do not automatically mean physical reality. Many of these solutions rely on ideal conditions that may not exist in nature. Some would require exotic forms of matter with unusual properties, materials that push outward with negative pressure rather than pulling inward through gravity. At present, no evidence suggests that such stable wormholes exist in the real universe. Still, studying these mathematical structures has deepened our understanding of spacetime. They show that the geometry described by Einstein's equations can be far richer than our everyday experience suggests. Another unusual idea sometimes discussed in connection with black holes is the concept of a white hole. If a black hole is a region of spacetime where nothing can escape, a white hole would be the opposite. Matter and light could leave a white hole, but nothing could enter it. In theory, the equations of general relativity allow solutions that resemble these objects, but like wormholes, white holes remain purely hypothetical. Astronomers have never observed any evidence that they exist in the universe. Most physicists suspect that such structures are unstable or impossible to form under realistic conditions. Nevertheless, these possibilities reveal something important. Black holes sit at the intersection of several fundamental ideas in physics: gravity, space-time geometry, energy, and information. The deeper scientists explore these ideas, the more they discover that black holes challenge our assumptions about how the universe works. For example, the mathematics describing rotating black holes sometimes suggest that their interiors may contain multiple horizons, nested boundaries that separate different regions of space-time. Each horizon represents a transition in how light and matter move. These layered structures hint that space-time near a black hole may behave more like a complex landscape than a simple gravitational well. But once again, these predictions rely on equations that may break down near the singularity, where the curvature of space-time becomes extreme. Until physicists develop a theory that combines gravity with quantum mechanics, the true structure of black hole interiors will remain uncertain. Yet despite all these mathematical curiosities, the black holes we observe across the universe are not exotic puzzles floating in isolation. They're born in real astrophysical events. Massive stars collapse under their own gravity. Galactic centers accumulate enormous reservoirs of matter. Black holes merge, collide, and grow over billions of years. To understand the role they play in shaping the cosmos, we now turn our attention away from abstract equations and toward the life cycles of stars. Because every stellar mass black hole begins with a star, an enormous sphere of gas shining with nuclear fire. And when that fire finally fades, gravity takes over. Until now, we have explored black holes mostly through the lens of mathematics and geometry. We've seen how space-time bends, how horizons form, and how rotation twists the surrounding universe. But black holes are not just solutions written on chalkboards. They're born in the violent endings of real stars. To understand how a black hole forms, we must begin much earlier, long before the collapse, when the star itself is still shining. A star is in many ways a delicate balance. Gravity constantly pulls its matter inward, trying to compress the enormous sphere of gas toward the center. At the same time, deep within the star's core, nuclear reactions release tremendous energy. These reactions push outward, creating pressure that resists gravity's pull. For most of a star's life, these two forces remain in equilibrium. Gravity pulls inward, radiation and pressure push outward. As long as the balance holds, the star shines steadily. Our own sun is currently in this peaceful phase. It has been shining for about 4.5 billion years, and it will continue doing so for several billion years more. But the fuel that powers a star is not endless. At the center of a typical star, hydrogen atoms combine together through nuclear fusion. In this process, lighter atomic nuclei merge to form heavier ones, releasing energy as they do so. The energy produced by this fusion reaction travels outward through the star, eventually escaping into space as light and heat. Over millions or billions of years, however, the hydrogen fuel in the core slowly runs out. As the supply diminishes, the delicate balance between gravity and pressure begins to shift. Gravity gains the upper hand. The core of the star contracts under its own weight, growing hotter and denser as it shrinks. This rising temperature allows new fusion reactions to begin. Helium can fuse into heavier elements such as carbon and oxygen. For a time, this renewed fusion restores the balance, but each new stage of fusion produces elements that release less energy than the previous stage. Eventually, the core begins producing elements like silicon and iron. An iron marks a turning point in the life of a star. Unlike earlier fusion reactions, the formation of iron does not release energy. Instead, it consumes energy. This means the nuclear engine at the star's center can no longer support the weight of the outer layers. The pressure that once pushed outward fades. Gravity, patient and relentless, finally takes control. When this happens in a very massive star, one many times heavier than our Sun, the collapse begins suddenly and dramatically. The core shrinks at astonishing speed. Within a fraction of a second, matter that once spanned thousands of kilometers can compress into a region only a few dozen kilometers across. As the core collapses, electrons are forced into atomic nuclei combining with protons to form neutrons. This transformation releases a flood of ghost-like particles called neutrinos, which stream outward through the star. At the same time, the outer layers of the star begin to rebound violently from the collapsing core. The result is one of the most powerful explosions in the universe, a supernova. For a brief period, the exploding star can outshine entire galaxies. Shock waves rip through the surrounding gas, scattering heavy elements into space. These elements, carbon, oxygen, iron, and many others, will eventually become part of new stars, planets, and perhaps even living beings. But while the outer layers of the star explode outward, the core continues to collapse inward. And what happens next depends on the mass of that remaining core. If the core is not too massive, the collapse stops when the neutrons themselves begin to resist further compression. Neutrons, like electrons, obey the strange rules of quantum physics. They cannot all occupy the same state at the same time. This quantum resistance creates a new kind of pressure known as neutron degeneracy pressure. This pressure can halt the collapse, leaving behind a dense object called a neutron star. Neutron stars are incredibly compact. A single teaspoon of neutron star material would weigh billions of tons on Earth. Yet even neutron degeneracy pressure has its limits. If the collapsing core is too massive, gravity overwhelms this final resistance. The neutrons themselves are squeezed closer and closer together. At some point, no known force can stop the collapse. The core continues shrinking. The curvature of space-time grows deeper and deeper. Eventually, the collapsing matter passes within the critical boundary where escape becomes impossible. At that moment, an event horizon forms, and the star's core becomes a black hole. From the outside, the violent collapse disappears behind the horizon. The black hole settles into the simple structure we discussed earlier, defined primarily by its mass and rotation. But the birth of that black hole was anything but simple. It was the final act in the long life of a massive star, a life that began with clouds of gas drifting through space and ended in one of the most dramatic events the universe can produce. And while stellar explosions create many black holes across the cosmos, they are not the only way these mysterious objects can grow. Once formed, black holes can continue gaining mass by feeding on surrounding matter. They can merge with other black holes in powerful cosmic collisions, and over millions or billions of years, some of them grow to astonishing sizes at the centers of galaxies. Before we explore how that growth happens, we must first look more closely at the final limit that determines whether a collapsing star becomes a neutron star or continues collapsing into a black hole, because nature draws a boundary between those two outcomes, and crossing that boundary marks the moment when gravity truly becomes unstoppable. In the previous session, we followed the dramatic final moments of a massive star. The nuclear reactions that once held gravity in check eventually run out of fuel, the core collapses, and a tremendous supernova explosion sends the star's outer layers flying into space. Yet the fate of the core itself is not always the same. Sometimes the collapse stops, other times it continues without limit. To understand why, physicists had to explore a subtle boundary hidden within the laws of nature, a limit that determines whether gravity can be resisted or whether it becomes unstoppable. This boundary is known as the Tolman-Oppenheimer-Volkoff limit. Because that name is quite long, scientists often shorten it to something simpler, the TOV limit. The idea behind this limit is easier to understand than its name might suggest. Imagine compressing matter more and more tightly. At first, ordinary forces between atoms resist the compression. The electrons surrounding each nucleus create pressure that keeps atoms from occupying the same space. But under extreme gravity, such as the gravity inside a collapsing star, those ordinary atomic structures begin to break down. Electrons are squeezed into atomic nuclei, combining with protons to form neutrons. The matter in the core becomes what physicists call neutron-rich matter. At this stage, a new kind of resistance appears. Just as electrons cannot all occupy the same quantum state, neutrons follow similar rules. Quantum mechanics forbids identical particles from crowding into exactly the same configuration. This rule creates a powerful form of pressure known as degeneracy pressure. Degeneracy pressure does not come from temperature or motion. Instead, it arises from the fundamental structure of quantum mechanics itself. Even at extremely low temperatures, this pressure can remain strong. For neutron stars, degeneracy pressure becomes the final defense against gravity. If the core of the collapsing star is small enough, usually around 1.5 to 2 times the mass of our Sun, this quantum pressure can halt the collapse. The star settles into a neutron star. But if the core becomes more massive than that threshold, gravity grows too strong. The neutrons are forced closer together. The quantum pressure that once resisted collapse can no longer keep up. At that point, the core passes the TOV limit, and when that happens, something extraordinary occurs. No known force in nature can stop the collapse. The matter continues compressing inward. The density grows greater and greater. The curvature of space-time deepens, and eventually the collapsing core shrinks within the boundary that defines a black hole. The event horizon forms. From the outside universe, the collapse seems to slow dramatically as it approaches that boundary. Light escaping from the shrinking star becomes increasingly stretched and reddened. Clocks near the surface appear to tick more slowly. To distant observers, the final stages of the collapse appear almost frozen in time, yet from the perspective of the collapsing matter itself, the process continues normally. The star's core crosses the horizon and disappears from the observable universe. Inside that boundary, the fate of the matter becomes one of the deepest mysteries in physics. Some models suggest that the matter continues collapsing toward a singularity, a region where the curvature of space-time becomes infinitely strong. Other ideas propose that quantum effects may eventually halt the collapse at extremely small scales, but at present no complete theory describes exactly what happens inside a black hole. Still, the existence of the TOV limit helps scientists understand an important transition. Below the limit, gravity can be resisted. Above the limit, gravity wins. This boundary is not merely theoretical. Astronomers can actually observe its consequences by studying neutron stars and black holes across the universe. For example, neutron stars are incredibly dense, but they also have a maximum mass. Observations show that neutron stars rarely exceed about 2 times the mass of our Sun. Objects heavier than that threshold tend to collapse into black holes instead. In this way, the universe itself appears to follow the predictions of the TOV limit. The boundary between neutron stars and black holes emerges naturally from the laws of physics. Yet even after a black hole forms, its story does not end. Black holes are not static relics of collapsed stars. They interact with their surroundings. Gas, dust, and even entire stars can fall toward them, forming swirling disks of matter that glow brightly as they spiral inward. Sometimes 2 black holes drift together through space and eventually merge in a powerful collision. When that happens, enormous ripples spread outward through spacetime itself. These ripples are known as gravitational waves. In 2015, scientists detected these waves directly for the first time using an instrument called the Laser Interferometer Gravitational Wave Observatory, often abbreviated as LIGO. The signal came from the merger of 2 black holes more than 1 billion light-years away. As the 2 objects spiraled together, they released vast amounts of energy in the form of gravitational waves, brief distortions of space-time travelling across the cosmos at the speed of light. For a moment, the power released in that collision exceeded the combined brightness of all the stars in the observable universe. And yet, the event occurred silently in the darkness of space, leaving only faint ripples that sensitive instruments on Earth could detect. The discovery of gravitational waves opened an entirely new way of observing black holes. Instead of relying only on light, astronomers can now listen to the subtle vibrations of space-time itself. Through these signals, scientists can measure the masses of black holes, their spins, and the violent dances they perform before merging. These observations reveal that black holes are far from rare. They are scattered throughout galaxies, quietly shaping the cosmic landscape, and some of them, through a long history of growth and mergers, have become unimaginably large. In the next part of our journey, we will explore those giants, black holes millions or even billions of times heavier than the Sun, lurking at the centres of galaxies. Because the story of black holes does not end with the collapse of a star. In many ways, that is only the beginning. The black holes formed from collapsing stars are already remarkable objects. A single stellar black hole may contain several times the mass of our Sun compressed into a region only a few dozen kilometers across. But in the centers of many galaxies, astronomers have discovered something far larger. These objects are known as supermassive black holes. Instead of weighing a few times the mass of the Sun, they can contain millions or even billions of solar masses. To imagine the scale of this difference, picture the Sun as a single grain of sand. A stellar black hole might contain 5 or 10 grains of sand, but a supermassive black hole could contain an entire mountain made of those grains. And yet all of that mass is hidden within a region of space smaller than the orbit of many planets. The existence of these enormous objects was once only a theoretical idea. Today, however, astronomers have gathered powerful evidence that nearly every large galaxy contains one at its centre. Our own Milky Way galaxy is no exception. At the very heart of the Milky Way lies a supermassive black hole called Sagittarius A star. Scientists pronounce its name as Sagittarius A star, even though the symbol used in astronomy is the letter A followed by a small star. This black hole contains about 4 million times the mass of our Sun. Although it is enormous by human standards, Sagittarius A star is relatively modest compared with some of the giants found in other galaxies. In certain distant galaxies, supermassive black holes may contain billions of solar masses. Understanding how such enormous objects form remains one of the most fascinating puzzles in astrophysics. One possibility is that they begin as smaller black holes created when massive stars collapse. Over millions of years, these black holes slowly grow by pulling in surrounding matter. Gas drifting through the galaxy can spiral toward the black hole, forming a swirling disk around it. This structure is known as an accretion disk. Within the accretion disk, matter moves at incredible speeds. As the gas spirals inward, friction and magnetic interactions heat it to extremely high temperatures. The disk begins to glow brightly, often shining with more energy than all the stars in the surrounding galaxy. In the most extreme cases, this glowing region becomes what astronomers call a quasar. Quasars are among the brightest objects in the universe. Although they appear star-like in telescopes, they are actually the blazing centers of distant galaxies powered by supermassive black holes devouring matter. The energy released in these systems can be astonishing. As matter falls toward the black hole, a portion of its mass is converted into energy. This conversion follows a principle discovered by Albert Einstein, the relationship between mass and energy. In scientific notation, this idea is written as the famous equation E equals m times c squared. To make that expression easier for the ear to follow, we can say it in words. Energy equals mass multiplied by the speed of light, multiplied again by the speed of light. Because the speed of light is extremely large, even a small amount of mass can release tremendous energy when converted in this way. Near a black hole, the process of accretion can transform matter into radiation with remarkable efficiency. In fact, the energy released by matter falling into a black hole can exceed the efficiency of nuclear fusion inside stars. That is why quasars shine so brightly across the universe. But supermassive black holes do more than simply glow. They also shape the galaxies around them. Observations have revealed an intriguing relationship between the mass of a galaxy's central black hole and the size of the galaxy's bulge of stars. This relationship suggests that black holes and galaxies grow together, influencing each other over billions of years. When a supermassive black hole feeds actively, it can release enormous jets of energy that blast outward into the surrounding galaxy. These jets can heat interstellar gas and sometimes push material away from the galactic center. In this way, the black hole may regulate how quickly new stars form. Too much gas falling inward can trigger powerful feedback from the black hole, which then slows the growth of the galaxy. Too little gas allows the galaxy to evolve more quietly. This delicate balance between feeding and feedback may explain why galaxies take the shapes we observe across the cosmos. Even more dramatic events occur when galaxies themselves collide. Over cosmic time, galaxies often merge with one another, drawn together by gravity. When this happens, the supermassive black holes at their centers begin a slow and intricate dance. They spiral around each other for millions of years, gradually losing energy through gravitational waves. Eventually, the two black holes merge into a single larger giant. The final moments of this merger release enormous ripples through spacetime, gravitational waves powerful enough to travel across billions of light years. Future observatories are expected to detect these waves from supermassive black hole mergers, opening another window into the hidden lives of galaxies. In recent years, astronomers have even managed to capture the first images of black holes themselves. Using a worldwide network of radio telescopes known as the Event Horizon Telescope, scientists combined signals from observatories across the Earth to create a virtual telescope the size of our planet. With this instrument, they photographed the glowing ring of light surrounding the black hole at the center of the galaxy M87. Later, they produced a similar image of Sagittarius A star in our own galaxy. These images reveal the shadow cast by the event horizon as light bends around the black hole. They offer direct evidence that these strange objects truly exist. Yet despite all these observations, black holes continue to challenge our understanding of physics. The deeper we study them, the more they seem to sit at the crossroads between gravity, quantum mechanics, and the nature of information itself. And it is within this crossroads that one of the greatest mysteries in modern science emerges, because black holes do not simply trap matter and energy forever. According to quantum physics, they may slowly lose energy over time. In fact, they may even evaporate. The idea that black holes could gradually fade away would have surprised Einstein himself. But it emerged from an unexpected insight discovered in the 1970s by a physicist named Stephen Hawking, and that insight would open an entirely new chapter in the story of black holes. For a long time, black holes seemed like the ultimate cosmic traps. Anything that crossed the event horizon was gone forever. Matter disappeared inside. Light could not escape. Even time itself behaved strangely near the boundary. According to classical physics, the version of physics that existed before quantum theory, black holes were perfectly silent objects. They swallowed energy, but they did not give anything back. Yet in the early 1970s, a surprising idea began to emerge. It came from a young physicist named Stephen Hawking. Hawking was studying what happens when the laws of quantum mechanics are applied near the edge of a black hole. At first, this might sound like a small technical question, but it led to one of the most astonishing discoveries in modern physics. To understand the idea, we first need to look briefly at how quantum physics describes empty space. In everyday life, we imagine empty space as truly empty, nothing there at all. But quantum physics paints a different picture. According to quantum theory, what we call empty space is never completely still. Even in a perfect vacuum, tiny fluctuations constantly appear and disappear. These fluctuations arise from the strange uncertainty built into quantum mechanics. Energy can briefly appear in very small amounts, as long as it disappears again almost immediately. Physicists often picture these fluctuations as pairs of tiny particles that appear together and then quickly vanish. One particle carries positive energy, the other carries negative energy. Under normal circumstances, these pairs form and disappear so quickly that they leave no lasting trace. But something unusual happens near the event horizon of a black hole. The intense curvature of spacetime can separate these pairs before they have time to disappear. Imagine two tiny particles suddenly appearing just at the edge of the event horizon. One particle falls inward into the black hole, the other escapes outward into space. If the pair separates in exactly this way, the escaping particle can become real rather than disappearing again. To an observer far away, it appears as if the black hole has emitted a tiny particle. This phenomenon is known as Hawking radiation. The name comes from Stephen Hawking, who first calculated the effect while studying the interaction between gravity and quantum fields. The radiation itself is incredibly faint. A black hole does not glow brightly like a star. Instead, it releases a very weak trickle of particles over extremely long periods of time. For large black holes, the effect is so small that it is almost impossible to detect with current technology, yet the theoretical implication is profound. Black holes are not completely black, they slowly lose energy. And because energy and mass are related, losing energy means losing mass. Earlier we discussed Einstein's famous relationship between energy and mass. In words, the relationship says that energy equals mass multiplied by the speed of light multiplied by the speed of light. When a black hole emits Hawking radiation, it is effectively converting a tiny portion of its mass into energy that escapes into space. This means that black holes can gradually shrink over time. The process is extremely slow for large black holes. A stellar black hole with several times the mass of our Sun would take far longer than the current age of the universe to evaporate completely. But smaller black holes would disappear more quickly. As a black hole loses mass, something interesting happens. Its temperature increases. This may seem counterintuitive. Most objects cool down as they lose energy. Black holes behave differently. The smaller the black hole becomes, the hotter its Hawking radiation grows. As the evaporation continues, the radiation becomes stronger and stronger. Eventually, at least according to the theory, the black hole could end its life in a brief burst of energy as the final remaining mass disappears. Whether this final stage actually occurs exactly this way is still an open question. Physicists do not yet fully understand the quantum structure of spacetime at such tiny scales. But the idea of Hawking radiation changed how scientists think about black holes. Before Hawking's discovery, black holes seemed like permanent features of the universe. After Hawking's work, they became dynamic objects with lifetimes. They could form, grow, interact with their surroundings, and eventually fade away. Yet Hawking radiation also introduced a deep puzzle. The radiation escaping from the black hole appears almost completely random. It does not seem to carry detailed information about the matter that originally fell into the black hole. Imagine throwing a library of books into a black hole. The pages, the ink, the stories, all of it disappears beyond the event horizon. If the black hole later evaporates into a cloud of simple particles, where did the information describing those books go? Did it vanish completely, or is it somehow encoded in the radiation in a way we do not yet understand? This question became known as the black hole information paradox, and over the past several decades it has become one of the most important problems in theoretical physics. Because according to quantum mechanics, information should never truly be destroyed. But black holes seem to suggest the opposite. Resolving this contradiction may require a deeper understanding of how gravity and quantum mechanics fit together. And in the search for that understanding, physicists have begun exploring some of the most ambitious ideas about the nature of reality itself, ideas in which spacetime may not be fundamental at all. Ideas in which geometry and gravity might emerge from patterns of quantum information, and it is within this puzzle, the information paradox, that black holes may reveal their most important secret. The discovery of Hawking radiation changed how scientists viewed black holes. Before Stephen Hawking's work, black holes were thought to be eternal. Once something crossed the event horizon, it was gone forever, trapped inside a gravitational prison from which nothing could escape. But Hawking showed that black holes are not completely silent. They slowly emit radiation, gradually losing mass over immense stretches of time. This realization brought black holes into the world of quantum physics, and with that step came a problem that has puzzled physicists for decades. The problem centers on something surprisingly abstract: information. In everyday life, information may seem like an intangible idea, but in physics, information has a precise meaning. Information describes the detailed state of a system, the arrangement of particles, their energies, their positions, and all the tiny details that define how matter is organized. According to quantum mechanics, information cannot simply vanish. If you burn a piece of paper, the paper appears to disappear. But the information describing the atoms in the paper does not truly vanish. Instead, it spreads into the environment, in the smoke, the heat, and the motion of surrounding air molecules. The information becomes incredibly scrambled and difficult to reconstruct, but it still exists in principle. This principle is deeply embedded in the mathematics of quantum theory. Quantum evolution is reversible. If you could track every particle perfectly, you could, in theory, reconstruct the past state of the system. But black holes seem to violate this rule. Imagine again that enormous library of books falling into a black hole. Each book contains countless pages, words, ideas, and patterns of ink. All of that structure represents information. When the books cross the event horizon, that information disappears from the observable universe. Later, as Hawking radiation slowly leaks from the black hole, the emitted particles appear almost completely random. They do not seem to carry any recognizable imprint of the books that fell inside. Eventually, the black hole evaporates completely. And if the radiation truly contains no trace of the original information, then the information is lost forever. This conclusion would contradict one of the most fundamental principles of quantum mechanics. Thus emerged the black hole information paradox. Two pillars of modern physics appear to disagree. General relativity describes black holes as objects that swallow everything beyond the event horizon. Quantum mechanics insists that information cannot be destroyed. Both theories have been tested extensively and work extraordinarily well within their domains. Yet when they meet at the edge of a black hole, they seem to give conflicting answers. For many years, physicists debated which theory might be incomplete. Some wondered whether information might truly be destroyed inside black holes. Others suspected that Hawking radiation must somehow carry subtle patterns encoding the lost information. The challenge is that Hawking's original calculations suggested the radiation was purely thermal, meaning it depended only on the black hole's temperature and not on the details of what fell inside. If that result were exact, information would indeed be lost. But losing information would have profound consequences. It would imply that the universe itself might evolve in ways that erase parts of its past history. That idea would require a major revision of quantum theory. Over time, most physicists came to suspect that quantum mechanics is unlikely to be wrong. Instead, they began searching for ways in which the information might escape after all. One important clue came from studying how entropy behaves during black hole evaporation. Entropy is a measure of disorder or uncertainty in a system. If information were truly lost during evaporation, the entropy of the emitted radiation would increase steadily until the black hole disappeared. But in the 1990s, physicist Don Page proposed a different possibility. Page suggested that the entropy of the radiation should follow a specific pattern over time. At first, the entropy would rise as the black hole emitted random-looking radiation. But after about half of the black hole's mass had evaporated, the trend would reverse. The radiation emitted later would begin to carry information about what had fallen into the black hole earlier. As a result, the entropy would eventually decrease again. This predicted pattern became known as the Page curve. In words, the Page curve describes how information might gradually leak out of a black hole as it evaporates. For many years, this idea remained only a theoretical proposal. But more recently, new calculations using advanced tools from quantum gravity have produced results consistent with the Page curve. These developments suggest that Hawking radiation may indeed contain hidden correlations, subtle relationships between particles that encode the lost information. However, exactly how this information escapes remains uncertain. The answer may require a deeper theory that unifies gravity with quantum mechanics. In that search, physicists have explored several fascinating possibilities. Some involve the idea that spacetime itself may be connected to patterns of quantum entanglement. Others suggest that information might be stored on the surface of the event horizon rather than inside the black hole. These ideas push the boundaries of how we think about space, time, and reality itself. Black holes, once thought to be simple cosmic traps, may actually be laboratories where the deepest laws of the universe reveal themselves. And in the next part of our journey, we will explore some of the bold ideas scientists are developing to solve this puzzle. Ideas that suggest space-time itself may emerge from the hidden structure of quantum information. The information paradox did something unusual in physics. Instead of solving a small technical problem, it forced scientists to rethink some of their deepest assumptions about the universe. For centuries, space and time were treated as the stage on which the events of the universe unfold. Planets move through space, stars explode in space, galaxies drift across space. But black holes began to suggest that space itself might not be the most fundamental ingredient of reality. Instead, something deeper may lie underneath. One of the first clues came from a surprising principle known as the holographic principle. The idea emerged from studying the thermodynamics of black holes, the way black holes store entropy and information. Earlier in our journey, we mentioned entropy as a measure of disorder or uncertainty. In black holes, entropy appears to be related not to the volume of the black hole, but to the area of its event horizon. This result surprised many physicists. Normally, information stored inside an object scales with its volume. A larger box can hold more objects than a smaller one. But black holes seem to behave differently. Their entropy increases with the surface area of the horizon. In other words, the amount of information describing a black hole appears to be encoded on its boundary. This strange observation inspired a radical idea. Perhaps the entire three-dimensional interior of a region of space can be described by information living on its two-dimensional boundary. Just as a hologram on a flat surface can produce a three-dimensional image, the physics inside a volume of space might emerge from information stored on its surface. This is why the idea became known as the holographic principle. Although the concept sounds abstract, it has found strong support within certain theoretical frameworks of quantum gravity. In these models, the geometry of space-time can emerge from patterns of quantum information encoded on distant boundaries. Another intriguing idea connects black holes with one of the most mysterious features of quantum physics: entanglement. Quantum entanglement occurs when two particles become linked in such a way that measuring one instantly influences the state of the other, even if they are separated by large distances. The connection does not involve signals travelling through space. Instead, the particles behave as though they are part of a single system. Some physicists have proposed that space-time itself might be built from vast networks of entanglement. According to this view, the smooth geometry we experience as space may emerge from deeper connections between quantum systems. A particularly bold idea combines entanglement with wormholes. This proposal is sometimes summarized by the phrase ER equals EPR. To say that phrase more gently for the ear, we can pronounce it as ER equals EPR. Here, the letters ER refer to Einstein and Rosen, the physicists who first described a mathematical structure resembling a wormhole. The letters EPR refer to Einstein, Podolsky, and Rosen, the scientists who studied quantum entanglement in the famous EPR paradox. The suggestion behind this idea is that entangled particles might be connected by tiny geometric links within space-time. These connections would not allow signals to travel faster than light, but they might reveal that geometry and entanglement are deeply related. If that idea is correct, the structure of space-time could arise from the web of quantum connections between particles. Black holes play a central role in exploring these possibilities, because black holes push gravity and quantum mechanics into the same extreme environment. They provide a unique testing ground for new theories. In recent years, physicists have used tools from quantum information theory to analyze how information flows in and out of black holes. These calculations have revealed subtle patterns suggesting that the radiation escaping from a black hole may indeed contain hidden correlations. Those correlations could carry the information that once seemed lost. Some recent studies even show how the Page curve, the pattern of entropy change we discussed earlier, can arise naturally within certain models of quantum gravity. Although these results do not yet provide a complete theory, they hint that the paradox may eventually be resolved. And if it is resolved, the solution could reshape our understanding of reality. Space may not be a fundamental backdrop. Time may not be an independent dimension flowing steadily forward. Instead, both may emerge from deeper relationships between quantum systems. In that sense, black holes may be more than mysterious astrophysical objects. They may be windows into the architecture of the universe itself. By studying what happens at their horizons, physicists are slowly uncovering clues about how gravity, information, and space-time are woven together. Yet even with all these discoveries, the story of black holes remains unfinished. Each new insight opens another question. Each new observation reveals another layer of complexity. And as we approach the end of our journey tonight, it becomes clear that black holes do not simply challenge the laws of physics. They invite us to look deeper, to ask whether the laws themselves are only part of a much larger story. As we come toward the end of this journey, it is worth pausing for a moment and stepping back from the details. Over the course of our exploration, black holes have taken us through many layers of physics. We began with gravity as the gentle bending of space-time. We followed massive stars through their dramatic collapse. We crossed the strange boundary of the event horizon. We peered toward the mysterious singularity hidden deep within, and along the way we discovered that black holes are not simply dark cosmic traps. They're also engines, laboratories, and perhaps even teachers. Because whenever scientists push their theories into the extreme environment near a black hole, something interesting happens. The theories begin to strain. General relativity, Einstein's elegant description of gravity, works beautifully for planets, stars, and galaxies. Quantum mechanics, the framework describing the microscopic world, works just as beautifully for atoms and particles. But near a black hole, where gravity becomes incredibly strong and quantum effects cannot be ignored, these two great theories begin to clash. This is why black holes have become one of the central puzzles in modern physics. They sit precisely at the boundary where our current understanding begins to break down, and yet, paradoxically, it's often at such boundaries that new discoveries emerge. History shows that whenever two successful theories collide, the tension between them can reveal deeper truths. The conflict between classical mechanics and electromagnetism eventually gave rise to Einstein's theory of relativity. The conflict between classical physics and atomic experiments gave birth to quantum mechanics. Today, the tension between gravity and quantum theory may be pointing toward another transformation. Physicists often call this missing framework a theory of quantum gravity. Such a theory would describe how space-time behaves at the smallest scales, where the geometry of the universe itself may fluctuate and change. In this deeper picture, space-time might not be perfectly smooth. Instead, it could resemble a kind of microscopic foam, with tiny fluctuations appearing and disappearing constantly. Distances and durations might become uncertain, just as the position and momentum of particles are uncertain in quantum mechanics. Although this idea is difficult to visualize, the mathematics of several candidate theories suggest that space-time could have a discrete structure at extremely small scales, far smaller than anything we can currently observe. Black holes offer one of the few environments where such effects might become relevant. Near the event horizon, the curvature of space-time grows intense. Inside the black hole, our current equations suggest the curvature may become infinite. But infinities in physics often signal that a theory has reached its limits. Just as classical physics failed when confronted with the atomic world, general relativity may fail at the singularity. A deeper theory could smooth out the infinities and reveal what truly happens in these extreme regions. Some researchers believe that information, rather than matter or space-time, might be the most fundamental ingredient of reality. According to this viewpoint, the universe could be described as an enormous network of information processing. Particles become patterns within that network. Forces become rules describing how information flows and interacts. And space-time itself may emerge from the structure of those relationships. If that idea sounds abstract, it is partly because we are attempting to describe reality using concepts that evolved for everyday experience. Our minds are comfortable thinking about objects moving through space, but the deeper layers of physics may operate according to principles that are less intuitive. Black holes push us toward those deeper layers. They challenge the idea that space and time are fixed backgrounds. They challenge the assumption that information can be hidden forever. They even challenge our understanding of what it means for something to exist inside or outside a region of space. And yet, despite all these mysteries, black holes remain part of the same universe we inhabit. They are born from collapsing stars. They shape the growth of galaxies. They send faint ripples of gravitational waves across the cosmos. And occasionally, with the help of telescopes spanning the Earth, we can even glimpse the glowing rings of light surrounding their horizons. These glimpses remind us that the universe is both stranger and more beautiful than we often imagine. Even in the darkest regions of space, the laws of physics are quietly at work. Sometimes those laws behave exactly as we expect. Other times, they hint that something deeper remains to be discovered. Perhaps one day, scientists will finally understand how gravity and quantum mechanics fit together. Perhaps black holes will reveal the architecture of space-time itself, or perhaps they will show that the universe is built from something even more surprising than space, time, or matter. For now, black holes remain one of nature's most intriguing riddles. They sit quietly in the darkness, bending light, shaping galaxies, and whispering clues about the hidden structure of reality. And, as we finish tonight's exploration, it is comforting to remember that curiosity, like gravity, has a gentle pull of its own. It draws us forward, question by question, discovery by discovery. Each new insight brings us a little closer to understanding the universe we call home. And perhaps somewhere far beyond the horizon of our current knowledge, the answers are already waiting. And so, we've reached the end of tonight's exploration. Whether your eyes are still open, or you're already floating somewhere between waking and dreaming, thank you for being part of this little journey. If you'd like to join me again for more gentle wanderings, you're always welcome to subscribe, or share this with someone who could use a peaceful pause. Time has a way of slipping through our fingers, but here, in this quiet moment, it's just you and the soft hush of rest. Sleep peacefully, wherever and whenever you may be.